Okay, so if you're watching this video, you probably want to know what stochastic matrices are and the likes of it. So a stochastic matrix is where each term is denoted as P, and because this is an I by J matrix, each matrix or each entry within the matrix is known as P sub I J. And in order to make a matrix stochastic, it has to be inclusively between 1 and 0. On top of that, each column within the matrix must add up to 1. So algebraically, if we were to add up each column to how many columns there are, the total amount of columns should be 1. And let's look at the matrix right here. From what we can see, we have an identity matrix with the nth order of 1, with the nth order of 3, and you're going to notice something. What does each column add up to? And is it a big deal that there's only zeros and ones? And the answer to those two questions is yes and yes. Because each column adds up to 1 and the entries within that matrix are between 0 and 1 inclusively, this matrix is stochastic. Now let's transition to further examples. Okay, so let's say we're given this matrix, a 4x4, and they're all fractions. That's okay. As far as we can tell, these fractions are between 0 and 1, so it satisfies the first rule determining a stochastic matrix. Now the next concern is whether or not each column adds up to 1. In the first column, 1/4 times 4 equals 1. And in the second column, we have to find a common denominator. And this should be 60. And this is supposed to be 13 over 60. And if we multiply 4 by 15, multiply 1/3. For 1/3, we multiply the 3 by 20 and the 5 by 12. We're going to notice that they are going to add up to 1. So for our sake, let's just get that out of the way. So for column 1, that becomes 12 over 60 plus 13 over 60 plus 20 over 60 plus 15 over 60. Do these values add up to 60? 12 plus 13 is 25. 25 plus 45 is... 12 plus 13 is 25. 25 plus 20 is 45. Plus 15 results in 60 over 60. Okay. Now for the third column, we have 3 entries of 1/3. So we know the third column results in a value of 1. And now we're concerned with the fourth column, consisting of 3 entries of 1/6 and 1/2. So if you multiply a half by 3 over 3, we get 3/6 plus the 3 entries of 1/6, resulting in the sum of 1 in the fourth column. So therefore, this matrix is stochastic. Okay, here's a shorter one. Each entry is between 0 and 1, so that's out of the way. And what about the columns? Do they add up to 1? Well, it doesn't take much math to figure that out. We can deduce the answer by observation. And it turns out each column results in 1, so this matrix is therefore stochastic. Now, what about this matrix? Well, each entry is between 0 and 1 inclusively. However, there's one error. Can you guys point out where that is? It turns out the first column doesn't add up to 1. And in order for a matrix to be stochastic, each column must have a sum of 1. Therefore, this matrix is non-stochastic. Okay, let's look at this matrix. Right off the bat, each entry is between 0 and 1. However, does each column have a sum of 1? Well, the second column of 3/4 plus a quarter creates a value of 1. So that checks things off. Now what about column 3? 1/4 plus 3, or 2/3. Does that really equal 1? Well, let's create a common denominator. Let's multiply 1/4 by 3/3 and 2/3 by 4/4. As a result, we get 3/12 plus 8/12, and that creates a value of 11/12. Okay. Well, it's close, but there's no cigars, so because the third row sum does not equal 1, this matrix is not stochastic. Okay, so let's look at one last example, 4x4 matrix. Right away we know that each entry is between 0 and 1, that's good. Now does each column add up to 1? So let's look at the first column. If we were to add up each entry within the first column, we get a value of 1. Yeah, based on observation, you guys can probably tell. But what about the other columns? Okay, let's look at column 2. We have 0.2, 0.3, 0.4, and 0.5. So if you do the math, it turns out it's not going to be equal to 1. 0.2 plus 0.3 plus 0.4 plus 0.5, that creates 0.5 plus 0.4 plus 0.5. Therefore, we get a sum of 1.4, as we have just demonstrated. And because this value does not equal 1 within the second column, this renders the matrix as non-stochastic. So when we're dealing with stochastic matrices, the given matrix P is denoted as the matrix of transition probabilities because it produces the probabilities of each possible type of transition within a population. And many types of applications involve a finite set of states of a population. For example, the amount of people that live downtown or in rural areas, the way people vote left, right, or center, or the electronics consumers buy, like Android, Motorola, or Apple. So at each transition within this matrix, each member in a given state must either stay in that state or change to another state. For probabilities in this case, this means that the sum of the entries in any column of P is 1, which we have diligently discussed with the matrices from before. And I just want to clear that out. And this might be reviewed too for you guys. It just helps to look at the fundamentals of what this video was centered around. Anyways, if you guys have any criticism, feedback, or further questions, I'm more than happy to provide the help you guys need. Thank you for watching, and stay tuned.